Now let's take a look at the different applications of the derivative as a rate of change, rectilinear motion, and related rates. So, more often than not, or previously, the derivative has been used to determine slope of the graph of the function at a specific point. And with that, that would also mean that we can use it to determine the rate of change, how fast or how slow one variable changes with respect to another variable. If the functional relationship between y and x is given by y is equal to f of x, and if x changes from x sub 1 to x sub 1 plus delta x, then y changes from f of x sub 1 to f of x plus f of x sub 1 plus delta x. So just like how we showed it before in the lesson about differentials, once, for example, your variable x, from the value x sub 1, it becomes x sub 2, which is equal to x sub 1 plus a certain value, delta x, which means change in x, right? That's differential, the change in x. So how much changes? There you go. Of course, since we have the function f, then f of x will also change from f of x sub 1 to f of x sub 2, and that would be the same as f of x sub 1 plus delta x. And the rate of that change would be given by the formula f of x sub 1 plus delta x minus f of x, that's new minus old, over x sub 1 plus delta x minus x, which is new minus old. And, x sub 1. X sub 1 gets cancelled, that's why we get this formula here for the average rate of change, because that's just the change from x sub 1 to x sub 2. So that change is the average between the two. Between the two values of x, x sub 1, f of x sub 1. Now, do take note that if, for example, that is this curve here, this is the point, let's say, x sub 1, comma, f of x sub 1, the first point, and this is the other point, x sub 1 plus delta x sub 1, delta x, comma, f of x sub 1 plus delta x, that's your other point, then that change is the average change from this to this. So the changes in between, we don't have much of an idea. Because all we do is average, or we just get the average of the changes between these points, between these 2 points. Now, if you want to get the change at a specific point, then we find the limit of that as delta x approaches 0. As the changes approaches 0, then that becomes very minimal, and the change becomes the instantaneous rate of change of y per unit change in x at x sub 1. So at that specific x sub 1, how fast or slow is it changing at that specific point? And the instantaneous rate of change can be computed as follows. If y is equal to f of x, then the instantaneous rate of change of y per unit change in x to x sub 1 is the derivative of the function at x sub 1, if it exists. So let's have a specific example. Specific examples. So in 1a, we are asked to find the average rate of change of a of x with respect to x as x changes from 4 to 4.6. So in number 1, we have, say, a square. Imagine this is the square that we are talking about. So as this square with 4 units with side x equal to 4 changes to 4.6. Excuse me. Let's say we have it's not that obvious, but if this changed to this, So we have this. So let's assume that this is there you go. So from the black, which has x equals 4, to the red box, which has x is equal to 4.6, how much is the average change, rate of change in that? And the drawing is not drawn to scale. I'm not good at drawing. So how much would be the average rate of change? How fast or slow on average did that change happen? And the average rate of change is computed by f of x of 1 plus delta x minus f of x of 1 over delta x. To compute for delta x, that is your change from x of 1 from x of 2 to x of 1. Technically, 4.6 minus 4 is equal to 0.6. So your average rate of change will be equal to f of 4.6 minus f of 4 over 0.6. And since this is a square, and area is the thing that we're talking about, that means we're going to have 4.6 squared minus 4 squared over 0.6. This will now give us an average value of around 8.6 square centimeters per change in centimeter. That's the unit. So that means when the square was enlarged from 4 to 4.6, the area was changing as 8.6 square centimeters per change in centimeter. Although we did not actually look for the area, but the 8.6 would be there. Alright, so let's now go to number 2. Let R, it's just there, so it's here. In number 2, we have let R be the radius of a circular metal plate of area A sub R square inches and circumference C of R inches. If heat is expanding the plate, find the instantaneous rate of change of AR with respect to R and C of R with respect to R, meaning it's D over dr. So there. So since we're looking for the instantaneous rate of change, we need to find the derivative. And since this is circular, we know that the area of a circle is equal to pi r squared in terms of the radius, and the circumference of a circle is equal to 2 pi r when it comes to radius. So finding the derivative of these functions, a prime of r will be equal to 2 pi r. We don't need to write dr because it says with respect to r, while for c prime of r is equal to 2 pi. What does this mean? This means that the instantaneous rate of change when your radius expands is given by 2 pi r, while your circumference will constantly expand by 2 pi units every time r would expand. That's what, sorry, this is A and this is B. That's what number 2 is telling us. Let's now go to number 3. So in number 3, we have a solid consists of a right circular cylinder and a hemisphere on each end. The height of the cylinder is twice its radius. If R is the cylinder's radius and V of R is the solid's volume, find instantaneous rate of change of the volume with respect to R. So, we have a circular cylinder with hemispheres on each end. And then we are told that height is twice, the height of the cylinder is twice the radius. If R is the cylinder's radius and V of R is the solid's volume, finds the instantaneous rate of change of V of R with respect to R. So first, what is the volume of this solid? The volume of the solid would be the volume of the cylinder plus the volume of the two hemispheres, which actually builds up to one sphere. The volume of a cylinder would always be given by pi r squared h, sorry, pi r squared h. Well, the volume of the sphere is 4/3 pi r cubed. The thing is, we need to write h as r because we're looking for v of r. This is where this comes in. The height of the cylinder is twice its radius. Because we know that h is equal to 2r, by solving, r is equal to h over 2. And that's what we replace. Sorry. We don't need to actually solve it. Let's backtrack that. We can simply substitute 2r here. So v of r will be equal to pi r squared times 2r plus 4/3 pi r cubed. So v of r will be equal to 2 pi r cubed plus 4/3 pi r cubed. Therefore, simplifying this, we are going to get v of r is equal to 10/3 pi r. So now that we have the volume of the hemisphere, we can now find its instantaneous rate of change by finding its derivative. So therefore, v prime of r will then be equal to, that's 10/3 pi, because that's also a constant, then the derivative of that will be p r squared with respect to r. This is cancelled. Therefore, the instantaneous rate of change of the volume with respect to r would be 10 pi r squared. So now let's have more examples of the derivative being considered as a rate of change. So we have number 1, we have a cold front. This approaching a college campus in such a way that the temperature T of t degrees Fahrenheit T hours after midnight is given by the function T of t is equal to negative of negative 400 minus 40t plus t squared, wherein t is in between 0 and 1. So for letter A, we're asked to find the average rate of change of T of t with respect to t between 5 a.m. to 6 a.m. So we're looking for the average rate of change. That would simply be t of 6 a.m. Before we do that, we first have to figure out what is t of 6 a.m. minus t of 5 a.m. minus t of 5 a.m. over 6 a.m. minus 5 a.m., which is technically 1 hour. Now 6 a.m. is 6 hours after midnight, so t would be equal to 6. 6 hours after midnight. Whereas t of 5, that's 5 a.m., so that would be 5 hours after midnight. There you go. So with that in mind, we're now going to get the average rate of change would be, here, t of 6 minus t of 5 all over 6 minus 5, which is technically equal to 1. So therefore, I'm going to leave how to solve t of 6 and t of 5 to you because it's technically evaluating the function. Now that would then be equal to 604 minus 575 over 6 minus 5. And that would then be equal to 29. Therefore, the average rate of change between that hour from 5 a.m. to 6 a.m. would be 29 degrees Fahrenheit per hour. So, for 5 a.m. to 6 a.m., the temperature is changing 29 degrees Fahrenheit per hour. Now, in letter B, we're asked to find the instantaneous rate of change. Instantaneous rate of change of t at 5 a.m. So, at 5 a.m. exactly, what was the rate that the temperature is changing? How fast or how slow it is. So, to do that, we need to find the derivative of t. So first, before we move that out, this one, if we're going to simplify that, that is actually equal to 400 plus 40t minus, 40t minus t squared. Therefore, finding the derivative of that, t prime of t will be equal to 4t minus 2t. So the derivative at 5 a.m., that's t equals 5. So t prime of 5 will be equal to 4t minus 2 times 5, which is equal to 4t minus 10, which gives us 30. Which would mean that exactly 5 o'clock, the change that happened is 30 degrees Fahrenheit per hour. And now let's move to number 2. So in number 2, if water is being drained from a swimming pool and V of t liters is the volume of the pool t minutes after draining starts, then V of t is equal to this given function. We are asked to find the average rate of change, and then how fast is the water flowing out of the pool 5 minutes after the draining starts. So let's solve for that. We have V of t. Oops, we move it here. So for 2a, V of t would equal to, we can already distribute the 250, and that would be 400,000 minus 750t minus 250t squared. So it would be easier. For A, we're asked to find the average rate of change which water leaves the pool during the first 5 minutes. So with that in mind, since it's the first 5 minutes, we're going to get the change in time, change of t is already equal to 5 because the first 5 minutes. So therefore, the average rate of change would be equal to v of 5 minutes minus v of 0. Well, we don't have anything to that one. It's v of 0 all over 5 because that's already changed in t. So I'm going to leave to you how to get v of 5 and v of 0. So that would be the solving rather, and that would be, so this would already be 390,000 minus 400,000 all over 5. And this will give us the average rate of change is negative 2,000 liters per minute. It's negative because it's draining. So therefore, for the first 5 minutes, how fast is the volume changing? It's negative 2,000 liters per minute. If we're now going to be asked what is the how fast is the water flowing out of the pool 5 minutes after the draining starts. So that would be the instantaneous rate of change at 5 minutes. So that will be v prime of 5. So first we have to find v prime of t. Let's put it here. So v prime of t will then be equal to negative 750. It's negative 750 minus 500 t. 500 heat. So therefore, V prime of 5 would simply be negative 750 minus 500 times 5. Therefore, at exactly 5 minutes after the water is coming out at negative 3,150 liters per minute. So that at that specific minute, the 3,250 liters were being drained out of the tube. So that's the start of how we treat derivative as a rate of change.